Okay, so this is probably gonna be the last day of late homework. There might be another one. I don't. My brain is just lapsing. You're gonna do 6 slits here. You're not gonna put into fraction because we're gonna be dealing with this today. Did you don't. And what you're gonna do here is what we've pretty much done in all the other stuff here. You're gonna plot a ratio of the total intensity compared to the intensity of one slit versus delta D. So it's gonna be just like what we did before. You're gonna draw the first phasor diagram for a minimum because you can actually draw that one easily. So there's just gonna be one phasor diagram you're gonna draw with the 6 slits, and then you're gonna give me all the other locations of the minimum. Okay, that makes sense. So I don't think you're gonna find out overly challenging. They're kind of fun to do. Okay, so we're looking at end slit interference. And I've been running around today, so I wasn't able to get well, you saw one of them before, but I'll set up a single slit for you on Tuesday. So you can see what a single slit diffraction pattern looks like. We're going to get into it today. And what were the features we had here? So we had this intensity of the total intensity compared to the intensity of one slit. There was this sine squared n delta V over 2 over sine squared delta V over 2. What is delta D? Did you get this stuff? I did. Okay. Did no daily homework? Yeah. Okay. And then you got the handouts too. How does the delta D how's it defined? Remember, we have these end slits like this. We have the slight coming out like this. D is this distance between all these. These are all D. Yeah. Okay, then how's this delta D defined? Okay. So we got this little perpendicular here. This angle here was theta. So my little path difference is
D sine theta.
D sine theta. The path difference is this D sine theta. But then you know our delta, our phase difference is this 2 pi lambda. How's your path difference? And so this is going to be your 2 pi lambda D sine theta. And where's theta in the lab? When you set this up, where's theta in the lab? Remember what we had? We had this little screen there. And there, remember the D's are very, very small compared to the L. So that's the center right here. This is my L. And then we have these interference patterns that look like this. Okay. How many slits would that be?
2, 1, 2 slits.
2 slits. Everyone agree? Okay, tell me why it's 3.
Oh.
There's 2 minimas.
Yeah.
Oh.
Minimum here, minimum here. So that's 2 minimum. Number of minimums between the peaks are n-1.
I had the wrong idea, but it was a n plus 1.
Okay. From here to here, this is my theta. That's your theta there. So how would you go about calculating, if you're in a lab, how would you calculate the theta? Where this is your screen.
Like take measurements with a yardstick.
Particularly what?
Like,
Turns out you measure a lot of things in the lab. Okay.
well, you just measure like the links that you have, like that. The opposite basically.
You measure peak to peak. Okay, so you would measure basically from the center here to wherever this point you want to measure. So y is wherever you want to measure along here.
Yeah.
Okay. And y is your distance on the screen. This is your L. So what do you know about y over L?
Tangent.
That's your tangent theta. Okay, so then you could your theta would be the inverse tangent, y over L, and then this theta here you could put in there to get your delta D. Now, If theta is very small, what can you do? As soon as you hear the word very small, what does that make you think of?
You assume 0 1.
No. Taylor expansion. Okay, so what is the Taylor expansion of a tangent?
Never heard of it. It's trig function.
I agree. With the Taylor expansion of. Greg,
Yeah, cosine, sine, cotangent.
and so I write the Taylor expansion as.
You just gotta do the Taylor expansion of sine of
That sounds like a great thing to do. So I have the tangent of theta is sine of theta over cosine of theta. And what is the Taylor expansion of sine of theta? Leading order term is? Wait, leading order term of sine of theta is?
1.
Okay, let's try again. Leading order.
0. Cosine theta.
Theta, thank you. Okay, what is actually, okay. Sine of x is what? Give it the first three terms.
X
X.
minus x to 3 over 3 factorial. X to the 5 over 5.
What about cosine?
0.
Is
1. Plus x to the x squared over 4 or 2 factorial.
It turns out they're different.
Oh.
Which one?
Over 2.
Plus.
X to the 4th over 4 factorial.
So the cosine is gonna go to
1.
1. So this is just gonna be theta. Right, so you can say, do a couple things. You can say tangent theta is approximately then theta, which is approximately then sine of theta. So I can just put this in here, so I can actually write this then as 2 pi over lambda d y over L. My delta d. Okay. That's what you could do there. Okay. Questions? But again, that's only if you have really small theta. This way here is actually the more accurate one. Okay. Any questions on that? Okay. And what did we say happens when this n becomes really, really large, like 1,000? What device do you have then?
Fraction grading.
You have a diffraction grading. And so if you look at a diffraction grading, just since we haven't done all of this. When n is very large. Under 1,000. You have a diffraction grading. Okay, so suppose you have a diffraction grading with, okay, so for those of you who have used them, how do they specify diffraction grading? They specify the number of lines per centimeter, usually. With a number of lines per centimeter. Okay. So for example, maybe as an example here, let's say you have 2,000 lines per centimeter. Okay, what does that mean? Okay, first of all, how do these things look? Fraction gradings. No, I mean, if I were to give you one, what does it look like?
Like a little, like a bunch of like small little holes, right?
You're not even that. What do they look like? It looks like clear plastic. It looks like I just cut out like cellophane or something and give you clear plastic. How can you tell you have a diffraction grading? You look up at the lights and you see colors. I'll set one of these up so you can actually see what it looks like. So if I give you a diffraction grating with 2,000 lines per centimeter, what does it mean? Is if you measured a centimeter on there, how many lines would you have? 2,000. So what would be the D then for that? What would be the D between, in other words, when I wanted to do this delta D, well, okay, we only can deal with the max ones in diffraction gratings. So it says 2 pi m, I'll call it n. That's your 2 pi lambda. You said it out. You like that. What's that putting for D?
2,000. Does that mean?
2000, 1 centimeter over 2000.
Yeah, you take the reciprocal of it. So if you take the reciprocal of this, be this 1 over 2,000 lines per centimeter here, and then so this would be 1 over 2,000 centimeters. Okay, that's what actually what you're putting for the D. Okay, that makes sense. And again, if you're doing spectroscopy, everything's done with diffraction gratings usually. So some elaborate ways being set up. That all makes sense. Now, what we want to start doing with is accounting for the width of the slit. The width of the slit we're going to call A, and this is going to be the fraction. So how do we account? The width. So recall the width of the slit. A. In other words, we're going to do these things. You know, D is going to be this distance here. D is the distance from your centers there of the slits. And this has then some slit width here, A. So what we want to do is start accounting for the width on the slit, A. So in order to do this, count for the width. A. We need fraction. So the center walks along the hall, but you know, goes through the hall. I know they're out in the hallway. How come? How do I get that? Why isn't it blocked?
Bounces off stuff.
Even if you didn't.
Doors open.
Well, okay, the doors actually has to be open. Yes, that's good. But you know, so you're talking like this.
Waves are too big for the atom.
So, you know, here you're already walking down the hallway like this, blah, 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 walking away like this, okay? If I'm here, I can hear you.
Yeah.
Why? What's going on?
Because the waves don't get like attenuated enough by the wall, so you can hear. No.
Right, these sound waves are coming out, you know, they're going in one direction, so you're gonna have some coming in here like this. What's gonna happen here is that the sound waves hitting here are gonna act as basically secondary, they're gonna act like a source producing new sound waves. So what you're gonna do, you're gonna get new sound waves coming out like this, and more sound waves coming out like this. What's gonna happen here is that eventually they're gonna shrink here. And that's a process of diffraction. And so I've printed out. I thought I'd just hand you cat videos, because that pretty much if you see a cat video or a cat picture, turns out there's no cats on the internet. So it's actually a really fun thing. So this is actually a picture of a diffraction. There's kind of two options. But one is this is without any explanation of it here. So if you look at this part here, you have a sound wave coming this way. Let me explain what this is. So the reason you can hear things around a corner is entirely due to diffraction. So if you look at the one picture here, okay, this is a wavefront. what this line represents here, this is basically lines of constant phase. So this is basically lines. Constant. Okay, so in other words, what that means here. If I had to draw a whole bunch of waves like this, if I draw this wave like this wave like this, and this wave like this. Okay, basically where I am in here is basically it's gonna be a phase. This is all phase. Remember, we have these sine kx plus or minus 90 waves here. We call this whole thing in here phase. What I can do is I can pick a fixed line on here, maybe here for no good reason. So this, well, this one looks like it's messed up a little. That was this point, this point, and this point basically have the same phase argument here. So this would be a wavefront. So what this represents here, this is basically lines of when it hits here, when that wavefront hits here, you're going to get this phenomenon here. So this light here can actually reach beyond that hole here, basically by the process of diffraction. So this is. That's what I want to talk about, basically how that works. Yes.
This is because the waves that go through the wall are slowed down.
Oh, there's nothing, so there's a hole here.
Oh, so it's just like
And I've drawn, I've changed my wavelength here quite a bit once we change this much. It would have the same. And more or less have the same symbol.
so are nothing going through the wall, they're just all going through the
That is from this little hole.
okay.
And that's going to be the diffraction phenomenon we want to see. So if you turn the page here. Okay, this was actually first what we're going to do is use actually what's called Huygens principle. Huygens was Danish. Actually no, I think he was Dutch. I don't know. Either way, we're going to pronounce his name. So I don't think it's actually pronounced Huygens, but it usually gets pronounced Huygens. I think I've heard is actually a terrible pronunciation for it, but it's like it's no worse than saying plank. You know, if you say plank's law or plank's constant, no one's going to look at you funny, at least here in the United States. Go to Germany, they might look at you as plank. Really, it was plank. So as you know, Huygens, we're going to call it Huygens. He has this idea here. It's really quite clever. And what I've done is that from the Brigham Young book, I printed out the chapter on diffraction here. We can't get through the whole thing because we're almost running out of class. The first few pages here, he sets up, I think, Huygens principle. Actually, I think pretty well. Well, it's now I'll go over some points here. We're going to analyze everything with phasor diagrams again. So the easiest way. Right. To understand it. Diffraction. Okay, is Huygens principle. And so that's what this little cartoon here is, is meant to show here. So what happens here is if here's your old, this is an old wavefront. So this is going to be moving like this. And what it's going to state is that every point on this wavefront here acts as the source of a new wave. Okay, so every point on the wavefront acts as a source of a new wave. And so what I try to do here is that what this represents here is that this dot right here, they draw a wave like this. So this is a wave being generated from this one here. Okay, it's acting like a point source. Then this point here then produces its own wave. This point here produces its own wave. This point here produces its own wave. This point here produces its own wave like this. And these waves here are going to interfere and you're gonna produce a new wavefront. So this is a new wavefront. Because again, it's gonna be a line of constant phase. And then what happens here, then each of these points on here. Then acts as the source of a new wave, and then you propagate this out. And so what they've done is that they've drawn, he's drawn two different cases here. One is if we have straight line wavefronts here, one if we have a circular wavefront. That. And so that's what this is showing. And then he's taken basically the slit. He's drawn little point sources here, and other pieces on the wavefront. He's drawn the various waves, and he shows how they interfere like this. And that's actually how diffraction works. That's the easiest way to describe it. That makes sense? So, a couple of things here. How would we do this?
I have a question.
Sure.
What is the like orientation of these waves?
Okay.
Are
The
they,
what-
like are they going?
Yeah, these are actually a point. So in other words, when we have a you should have a point source like this. They're gonna radiate out like this. So
Okay,
imagine
okay,
that's a point
That's
source.
what.
Okay,
Okay.
that's what the point source. So let me make that point. No point. No, I'm gonna type it in. Point. No. When do we say point source? Okay, we mean solving the wave equation. Okay, in spherical coordinates. Okay, so what we have here is that, remember, here's our wave equation like this. That's our wave equation. We're in spherical coordinates. What do we do with this? We write this in spherical coordinates. So we write this in spherical coordinates. If we have a little time, I'll show you what you get from that in a certain case.
Mhm.
What happens here? What happens that here's our source. Here's our point source. The amounts of distance here are the wave here, this F. There's a from right here, the F at this point here. The F of this R here, let's say F of T. It's going to be basically this e to the I, you know, R. Well, let's say minus of T over R.
Mhm.
That's what they look like.
Okay.
And then there's some amplitude here, so amplitude.
Is there a reason that we're using point sources, or is it just because?
That's actually Huygens principle. Is that every point of the wavefront acts as a
Oh.
point source.
Okay.
Okay,
Yeah.
that's the easiest way to actually. That's right. Okay,
Yeah. Thank you.
that makes sense.
Yeah.
So, the way we're gonna do it is phasor diagrams. And then I wanna go through it, and then I'll explain what they do in the book. So the easiest way. Okay, this starts getting ridiculously complicated fast, because I mean, really, really fast. The easiest way to study. To, let's say, develop, explore, understand. Our problem is with phasor diagrams. Or the slide. So we have this. This is okay. And we have light coming in this way. So here's our laser. Okay, well, according to Huygens, how many sources then do we have in the slit here?
2, 1. Wait.
Right, we'd have a wavefront like this. Wavefront, 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 wavefront.
You have 4 sources.
Oh, no, this is just the whole laser light.
Oh.
beam like this. So what did we say about each point of the wavefront? X is a point source. So how many would there be there? Effectively,
Infinite.
an infinite number. So what I can do here is I can actually take this one, so there's an infinite, effectively, number of point sources. So we're gonna break this up into a whole bunch of little point sources. So I'm gonna come over here like this. And I'm gonna imagine just breaking this up into a whole bunch of little slits. And I'm gonna draw a phasor for each of these little slits. So draw a phasor. For each little slit. So what am I gonna have? I'm gonna have the first phasor like this. That's my first phasor. And then it's gonna make some angle, phase angle with the second phasor. It's gonna make some angle with the second phasor like that. And then it's gonna make an angle, then that will make a phase angle with the next one, next one, next one, next one, next one. If I keep making these smaller and smaller and smaller, what is that diagram gonna become?
Circle.
It's gonna become part of, it's gonna, an arc. Okay. So this is gonna really go to some sort of arc like this. Okay.
If we have infinite source point, we can have these with phaser. So like, how does the arcs?
Well, okay, let's figure that out. So here's my first phasor. Meaning the light for the first phasor. And here'd be the light for my second phasor, my last phasor. Okay, so what would be the phase angle between my first phasor here? That guy, and my last phasor here, that guy. What would be that phase angle?
Without triangle.
Because I'm gonna drop my little perpendicular. I'm gonna call this theta. So what is my little path difference then?
D sine theta.
Not anymore. This is no longer D, it is A. So it's A sine theta. Okay. So what I'm gonna have is I'm gonna call this delta A, not to be confused with delta D, because it's the phase angle now connected with the width. It'll be this 2 pi lambda. That's the path difference. So this will be your 2 pi lambda. A sine theta. Okay. That makes sense? So what's the longest my phase, for what phase angle will my phasor be as long as it can be?
Theta equal 90 degrees.
Hmm.
No.
Okay, so what happens in this case here? This is then gonna be my E total. Okay, that's my E total phasor. What's the biggest I can make that?
Visible. Small.
Okay, so what happens if my delta D is 0? It's 90.
That's it is 0.
So how does my phasor diagram look? It's a straight line.
To make it as big as possible, we need to maximize this data, right?
No, so what we have here is that if delta A equals 0, again, the delta A is your phase angle between your first phasor and your last phasor. So if I look at the phase angle between my first phasor and my last phasor, so in other words, if I could somehow, here's my first, and here's my last. If I move this. So, okay. Oh. Here's my first phasor, and here's my last phasor up here. I take this down here. It's my delta. So if my delta A is 0, what's happening here? All these little phasors align like this. And it's just in a straight line like that. This is my delta A. Equals 0. Okay, so this right here, this is my E total. If I'm at some other delta A, I have this. This is my E total. But what do I know about this length here? This length here. I'll call this S. That's what this S is here. Okay, so you can see this is going to be smaller than that. So your intensity goes down. When would I have a minimum?
It makes a circle.
And it makes a circle. So if delta A is, what delta A do I need to make a circle?
360.
2 pi. Okay.
Yeah.
I'm gonna have this. This would be an intensity of 0 because basically your E totals. What else could I have for a 0?
No, 2 pi.
I could have 4 pi. Now this length here, this stays the same. So if I had 4 pi, what would this do? Kind of shrinking on itself a little bit. What happened here? I had my delta at 4 pi. Then I'd have once, twice like this. This would be an intensity of 0 as well. By delta D 6 pi, I'd have once, twice, 3 times like that. It keeps on getting smaller and smaller and smaller. So your minimum. For your minimum, these are going to be 2 pi. Okay. That makes sense. And what we want to do is we want to figure out what these are going to look like. So when you do these, we have a single set here. We have laser light coming in here like this. Here's your screen. And this right here is my center. That's my center. The question is, what do these patterns look like? These patterns are going to look like this. Okay, we want to figure out what that looks like. This region here, this is given a fancy name. This is called your central contraction maximum. Maximum.
That's your.
Okay. We want to figure out what that looks like. So I call the intensity here. There's a my graph this. This is delta A. I have this. This right here, this would be my delta A 2 pi. This is my delta A. Those right here, this is going to be the intensity over the intensity at 0. And the intensity over the intensity of 0 is going to be 1. And again, this is, I should say, 50. In other words, your center. So you're basically comparing the intensity at any point along that screen compared to the intensity at the center. So if you're at the center here, then you have to have, by definition, you have to have 1. That makes sense? This is an A. And this would be my delta A. Makes sense. I'm going to tell you what this ratio is, and then you're going to tell me how to get it. This ratio here. And I'll put a 1 here like this as well for 1 slip. This is 1 slip. This is going to be the sine squared delta A over 2 divided by delta A 2. Okay. This is the answer. So we will show You tell me how to do it. So instead of delta A equals 0, we have this. I'll call the C 0. And so we're going to say when delta A doesn't equal 0, we're going to have this. And this right here is my E total. And what do we know about this guy right here? This is my E naught. Okay. Makes sense. So I'm going to do the following. Okay, so I can pick some point here. I'm going to say from here to there is a point. And I'm going to say that this is delta A. Right, I can always do that. I can pick some point there, make that delta A. Fine.
Divide the triangle.
I think so. Let's divide this here. So now we have this triangle here.
You have now.
Delta A over 2. This is E naught over 2. And this is R. Hey, what did I say about E naught over 2?
It equals to R sine the thing.
Okay. Delta A over 2.
Yeah.
Okay.
I forgot about that.
Actually, I don't want to do that. No, okay. Listen to. I've been up since 2:30. My brain is shot.
Damn.
You got a lot graded. I reserve the right to retract this at any point. I don't think I'm even, we're not gonna even use this. But if you were to pick a point R, that's what you would have, okay? We're just gonna go to the picture over there. This is my E total. Now I can make a point here. This is R. I can now make that delta A. That I'm off to. We're in good shape here. We're all good. Okay, now complete the proof.
Draw a triangle, divide the triangle.
We divide our triangle.
I don't even know where we're going with that.
So this is E naught over 2. That's really not divided, is it? Particular. This is my delta A over 2. And this is my R. What can you say now?
R equals E, no, E naught.
E naught over 2.
Equals R sine delta A over 2.
Is it E total?
Thank you. Keep nice. Okay. What can you say about this?
Oh, that E equal what 2 like just delta A? No.
What is this?
E naught equals
Arc. This is an arc.
yeah,
Maybe an arc length, maybe like an S.
yeah,
This is part of a circle.
yeah.
It has a radius R. And then go here delta A. Right, so we have a circle here. This is R, this is theta, this is S. S equals R theta. So what can you conclude here?
E naught equal R delta
E naught equals R delta A.
yes.
Make sense? Now, let's go through and tinker with this form. I can now look at the ratio E total, which is 2R sine delta A over 2, and divide this by E naught, which is my R delta A.
ER cancel.
R cancels, and if there's only something I could do with that, crazy too. I can actually bring it down and divide the delta A by that. Now what? We're done. Square both sides. This gives me E total squared, B naught squared, equals the sine squared, delta A over 2, delta A over 2 squared. Now what's the ratio of these two things equal?
I total.
Yeah, I can multiply both sides, top and bottom by that 1/2 epsilon naught C. Then I could write this as the total at any point with the intensity at 0. And I'll set it for one slit. Okay. Pretty
Multiplying
slim.
by epsilon naught C.
Remember, because your intensity, but you want epsilon naught C,
Oh, yeah.
E squared. So multiply the top and bottom of that factor in Shazam.
Right.
That makes sense? I have no idea why I was doing the triangle. No. Questions? Now, let's do n slits with width. Well, how do we account for n slits width? So now we have this. N of these, so this is D. This is A. Now n slits. Give me a hint, we're done. They didn't have width, what do we have? So for no. Yeah, I equals I1, the intensity of one slit times the sine squared of n delta D over 2. Sine squared delta D over 2. That's when we're not worrying about the width. Hey, but do we know anything about this guy? Yeah, that's our buddy there. It's hopped on up in here and Shazam, we're done. The intensity then at the one slit at 0. Now I'll move this here. No, I'll move it. It's going to be your sine squared delta A over 2. Delta A over 2. And squared. How's my buddy here? Boom.
This is beautiful equation.
Actually, it is.
Give me simplify.
No, that's what it goes to.
Oh, yeah.
Now, how does that look? What's the maximum value this can have? Or slits, or a single slit? Can have a maximum value of. What's the maximum value this thing can have? Your delta A is 0. What do you get? Mhm. Okay, so first of all, what is 4? What is I1 at that equals 0? That's the intensity at the very center. Okay, my delta A is 0, my theta is 0. So if I compare the intensity at the center to the intensity at the center, I get 1. The maximum value this can have is 1. Now, this, remember, I think I mentioned sometimes in class that everything in Calc 1 you use, in Calc 2 you use. You might say, well, wait, there's something in Calc 2 we've never used. Okay. You do. Okay, well, let's do this. If I want to know what happens when delta equals to 0, you might go, oh no, there's a problem. What's the current problem?
In the denominator.
I'm putting a 0 in the denominator. Turns out that that's not usually good. Okay. Now, give me a couple ways to fix this.
Limit.
Okay, you could use L'Hopital's rule. That's one way to do it.
Derivative.
If you do L'Hopital's rule on this, and how do you do L'Hopital's rule? Take the derivative of the top and divide it by the derivative of the bottom until you get something that's flat. Okay, so you can do it that way. But now, we're all grown up. Okay, so that's just showing that you do use everything in Calc 1 and Calc 2, even L'Hopital's rule. But now we're all grown up. And let's recall our 4 most important math techniques.
Multiplying by 1.
Multiplying by 1. Okay.
Separation of variables.
Separation verb.
Adding 0 and clarification.
Adding 0 and coefficient.
I was gonna say multiplying by 0.
Taylor expansion? Taylor expansion. Which one do we use here?
Separation of variables.
No.
Taylor expansion.
Taylor expansion. If my delta A is small,
Oh, yeah.
this is my top. What is the sign of x if x is small?
Essentially, yes.
X. Okay, so the delta, if I have sine of delta A over 2, then I score that. If delta A is small, what is the sign of delta A over 2?
X squared.
Delta A over 2. If it comes in squared, what happens? They cancel each other. That's good. That makes sense? Okay, kind of nice. Okay, so for that said, let's actually make a graph of this. So let's do 3 slides. Let's do 4 slides. 4 slides. Graph. So I'm going to plot the intensity here. Compared to the intensity of one set. This would be my delta D. So let's not put in the let's not put in this factor here. Let's ignore this factor first. So what would this look like?
Did I have a peak with that?
I have a peak in the center, and that peak would be what? I'm not putting the width. I'm getting to know this one.
1.
I have 4 slides.
Oh, no, no, no. 1 before. 4. 5. And 2.
Okay, what does my phasor diagram look like at delta D is 0 for 4 slides?
Oh, it's 60 by 1.
1, 2, 3. Right? So, if this is E1, they're all the same at 40. What's my intensity then? 16 on it. So this is going to be 16. I got another 2 pi here, 4 pi. 2 pi. 4 pi. What are you going to do? How many minutes between? 3. We're going to have 1, 2, 3, boom, 1, 2, 3, boom. So that's what I'd have. Now, what does this term here look like? There has this maximum value here with 1. Okay, and then it comes out, it's kind of drawn like this. Okay. So if I multiply those two together, what's going to happen? I'm going to have exactly this graph here, but it's going to be basically multiplied by this graph here. So what I'm going to do is I'm going to draw this graph here. I'm going to do a couple of things here. So here's my 16. I'm going to draw the fraction pattern like this. So that's my single step diffraction pattern. And then I'm gonna draw all this curve in here, but I'm not gonna have it exceed this value here, because this value, the maximum value of this value here is 1. Everything else is smaller, so I'm just gonna have to be less than that. So then I have something that looks like this. 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here, 1, here. 2, 3 here. Then same on the side. That makes sense? Now, what we'll ask tomorrow is that if we look at the center of diffraction max, if we look in here, how many peaks? And what we'll do, I'll show you how to calculate that. All it does is depend on the number of slips, the D, the A value. If you know those, you can actually determine how many of these things you're actually going to get. That makes sense? So if you have one of these, where is it? This right here corresponds to, right? This corresponds to delta D equals 2 pi. What does this point here correspond to?
Delta A equals 2.
Now this is going to be my delta A equals 2 pi. Yeah. And then from that information, we can actually calculate this. So actually, just by looking at one of these patterns here, you can actually determine the D, A value, and you can determine a lot of things just by looking at that. You know, the incident like that. And get a lot of information. Make sense? Have a good day.